Hi everyone, my name is Jiaqi, and today I will present our work can fully homomorphic encryption support general AI computation, functional and cost analysis. Let's start with the big picture. Today we are knowing how to protect data at rest. We encrypt our databases and disks. We know how to protect data in transit. TLS is everywhere, but data in use, data being actively computed on by a server, remains exposed. Memory scraping, side channels, and untrusted cloud operator. At the moment of the computation, the data is in plain text. Fully homomorphic encryption closes exactly this gap. The server evaluates a function directly on the server task and never sees the plain text at all. Here is the workflow concretely. The client encrypts its input and sends only server text to the cloud. The server evaluates the function homomorphically and sends back an encrypted result, which only the client can decrypt. Notice two properties. It's end-to-end. The secret key never leaves the client, and it's non-interactive. The client doesn't need to stay online and participate in rounds of the communication. This matters enormously for AI in sensitive domains, healthcare, finance, genomics. But here is the catch that motivates this whole paper. Real AI workloads mix two very different kinds of operations. On the one side, we have linear operations, matrix, multiplication, convolutions, and worldwide FHE schemes like BGV, BFV, and CKKS handles this very great. On the other side, the nonlinear operations, comparisons, ReLU functions, or sorting functions, bitwise schemes like TFTE handles those naturally. But look at any real workload here, neural network, convolution, then ReLU, then convolution, then max pooling. It consistently interleaves these two functions, supporting both kind of operations composed in any order without interaction. That is what we call computational generality, and it's a subject of our paper. Why is this hard? Because each scheme family is specialized. Worldwide schemes are fast on linear algebra and give you themed batching, but they struggle with nonlinear operations. You either approximate or pay for expensive polynomial interpolation. Bitwise schemes are the mirror image. Nonlinear operations are natural, but a single 16-bit multiplication takes around 30 seconds. So we ask two questions. First, functionality. Which FHE method can even support general computation non-interactively? And secondly, cost. When generality is available, what price do you pay? Prior SoCs have compared libraries and compilers. None has systematically examined the generality itself. Here's the definition. An FHE method has computational generality if it supports mixed linear and nonlinear operations composed in arbitrary sequences in a non-interactive and efficient manner. Two conditions matter. The conditions 1, mixed operations. The convolution, then ReLU, then convolution must compose seamlessly, with no format mismatch in between. Condition 2, non-interactivity. No round trips back to the client mid-computation. Only a handful of methods satisfy both. Our study has 3 stages: a functional survey of 10 FHE approaches with theoretical complexity analysis, workload micro benchmarks, 3 mixed operation building blocks, and 5 real privacy-sensitive applications, so the conclusions are both theoretical and empirical. This table is heard of our survey, so let me take a moment to walk through it. Each row is an FHE method. The columns come in 2 blocks. On the left, the cost of nonlinear operations comparison as the representative in multiplicative depth and complexity. On the right, the cost of linear operations, for example, the multiplications. The middle column marks themed support, and the final column is our verdict. Is the method fully general? Scanning top to the bottom, the first two rows are planned word-wise BGV, BFV, and CKS. The linear side looks great, depth one with seamed, but the nonlinear side is simply empty. They don't support comparison at all. The middle group are attempts to both nonlinear capability on two word-wise schemes: the polynomial approximation, polynomial interpolation, decomposed interpolation, XCMP, and the general functional bootstrapping. Their nonlinear column does get filled in, some with excellent complexity. The XCMP is even constant, but as we will see in the next slide, each pays for it elsewhere in exactness, special ciphertext formats, or limited input range. The composition is what breaks. The real answer is in the three highlighted rows at the bottom: the TFTE, scheme switching, and encoding switching. The only method with both sides of table checked, and note that the seamed column of the three, only encoding switching keeps seamed. Remember that detail if it foreshadows every experimental result that follows. In one side, why the other 7 failed. The CKS polynomial approximation is in exact near zero, unacceptable for genomics or finesse. The polynomial interpolation is exact, but its degree explodes with bitwise. The decomposed interpolation and the XCMP produce special format ciphertext that cannot fit into the subsequent linear operations. And the general functional bootstrapping is practical only up to about 12 bits. The common failure mode is that the optimized one operation type sacrifices seamless composition. A closer look at the three candidates. The TFT evaluated Boolean circuit gate by gate. Nonlinear is cheap, linear is costly. Scheme switching convert between word-wise and bitwise ciphertext, but the switch itself costs at least 2 to the B for B bits input. The encoding switching, the HE bridge approach, bridges two encoding within word-wise FHE and keeps seamed for both operation types. So one question drives everything that follows: does the method keep seamed? To compare them fairly, we designed 3 macro workloads capturing the canonical mixing patterns: the linear then nonlinear, the core of the database query; nonlinear then linear, the core of the decision trees and the graphs; and linear nonlinear linear, the core of the neural network layers, all single threaded over 128-bit security, 6 to 16-bit in precision. Two highlight results is that for the single operation, the TFT is quite competitive at a small bit width, while scheme switching cost explode at a precise growth. But once the workload is batchable, the amortized picture flips completely. Encoding switching seemed gives up to 14 times advantage over TFT and 25 times over scheme switching. The time is not the only cost. The TFT footprint is roughly 10 times smaller, under 5 megabytes of ciphertext versus nearly 15 or for the encoding switching. So there is a general trade-off. The TFT suits bandwidth constrained clients. The encoding switching trades memory for compute speed in data center settings. So we then validated these findings on 5 real applications: the graph shortest path, the decision tree sorting, database aggregation, and the neural network inference. Each maps onto one of our workload patterns. First, private shortest path. Taking the mean of the two paths is the comparison selection, the nonlinear then linear pattern. The key optimization here is encode the agency matrix row by row, so one operation updates an entire row. The V cubed drops to V squared complexity. On the 128 node graph, encoding switching about 660 seconds, TFT with no seam to exploit over 5,000 seconds. So decision trees node comparisons then product of the resulting bits along with the path. De Morgan rewrite turns that product into chip additions, cutting application depth. And since one input is compared against many thresholds, it batches perfectly. Encoding switching scales fast with the depth, while scheme switching pays conversions at every level. Sorting is a counterexample. Direct sort ranks each element and places it where the equivalent test, the m-squared mixed operations, all on one single array. No independent input means nothing for SIMD to exploit, and the ranking flips. The TFT sorts 8 elements in about a minute. Encoding switching needs 11, and scheme switching hours. This is does it keep SIMD question cutting the other way. So finally, the two worldwide friendly cases, the database aggregation is multiply, then compare over all rows at once. The perfect batching is at the 111 second for encoding switching and 512 rows versus 1600 for scheme switching, and the neural network inference exposes an accuracy versus latency frontier. Approximate CKS is fast but can drop below 80% accuracy. Exact general method holds accuracy but costs 10 to the 4 seconds and beyond. So everything distills into this flow chart. The only linear worldwide schemes, only nonlinear without SIMD, the TFT, the mixed without SIMD, like sorting using the TFT. Approximation acceptable, you can use CKS. Exact mixed computation with SIMD, you can use encoding switching. So thank you. Our code and benchmarks are open source on GitHub. I'm happy to take questions.